Let us take another example from the chapter of Newton's laws of says that the mass m, so this is one mass, is of the hanging block in the figure, prevent the smaller block from slipping over the triangular block. We have to find out this value of mass m. Now, in this particular problem, see what really happens. Let us consider this is tension in the string is T. And obviously tension here is also T. So this block mass capital M will start dropping down, will pull this block M dash or M prime towards right. And this will also, along with the block, this will also pull the block small m towards right. Say this acceleration is A. So this acceleration is also A. And this acceleration is also A if this smaller block does not slip over the slope. In fact, the problem says it will prevent the smaller block from slipping. That means the value of capital M will be such that the small block, small m, will not slip over and it will have the same acceleration with the main triangular block M dash. See how we solve this problem one by one. Take the one by one. We first consider capital M as the free body. Then what are the forces? We find the forces on them. This is capital M. This has a force going down is capital Mg, and there is a force upward of tension T. So from this three, we can easily write down the action-reaction equation. Since it is going down, it is also going down with an acceleration A. So downward force is capital Mg minus upward force is capital T is equal to its mass capital M into A. From here, we find that the T is capital Mg minus capital M. This is one equation. Let us preserve this equation. Let us say this is. Then we considered the triangular block M dash. Describe the forces on this triangular block. To draw it a little bigger, the understanding clear. This triangular block has a tension T, a force T. Also, this small block, small m, it says a reaction force on perpendicular to the surface. This angle is theta given. So this angle is theta, and so this angle is theta. big block, what we find? Say this force, reaction force applied by the small block, small m on the inclined surface. Let's say this is R, reaction force is R. Then the component of this force, horizontal direction is R sine theta. From this, we find the equation. We can write the equation T R equal to mass of this block is m dash into its acceleration a in this direction. It has acceleration a in this direction. Its mass is m dash. So start with this equation as say equation 2. And we look at the small block. This small block is also lying on a incline. Small block is also lying on an incline whose angle is theta. Whose angle is theta here. This also is lying on a incline. Now, this small block, let us say this block is here and its mass is, say, m. Its mass is small m. This small block will experience a reaction force from the triangular block perpendicular to the sides. And obviously, this reaction force and this reaction force is same. R and N are same. This is equal to R. These are the same in magnitude, though they are opposite in direction. Once again, then draw all the lines. This angle is theta, so this angle is theta. Right? Now, this vertical component of N counteracts the gravitational attraction force small in G. So that means from here we find, let's write R, actually N equal to R, let's put it this way, in magnitude, N equal to R cos theta is equal to G. And the horizontal component R sin theta maintains its acceleration of A. Therefore, R sin theta A. Dividing these two equations, we find that theta equal to G by A, or we find A equal to, this is one very important parent. Now let us look at equation, let's look at equation 2. Let's look at equation. From equation 2, what do we get from equation 2? Which is T minus, sorry, T minus R sine theta. Now R sine theta equal to m dash a. This was equation. Now, from here we find r sine theta is equal to small m a. That means t minus small m a equal to m dash a. Now, from equation 1, from equation 1, we get, from equation we get T is equal to mg minus ma. That means here we replace T by mg minus capital M A minus small m a is equal to capital M dash A. Or from here we get mg is equal to A within bracket capital M plus capital M dash plus. Right? Now we put the value of A from here. Therefore, mg is equal to g by cos theta multiplied by capital M plus capital M dash plus small. This g and g gets cancelled. So what do we get? So by cross multiplication, we get n cot theta is equal to capital M plus M dash. Capital M is multiplied by cot theta minus 1 is equal to M dash plus small m. So what we get? The value of capital M so that the small body does not slip over the triangular block is equal to capital M dash plus small m divided by the minus 1. So this is the answer. Let's go to the next question. Let's go to the next question. Here, once again, look at the question. Find acceleration of the blocks A and B. That means we have to find acceleration of blocks A and B in the three situations shown in the figure. Three situations are situation A, situation and situation B, and this is situation C. Let us consider the situations one by one. First, let us consider the situation 1. Situation A. First, let us consider situation A. Now, in situation A, you find the rope is fixed here, which comes down, it goes over this pulley, lower pulley, and then to the upper pulley, and then here. In fact, if you look at this arrangement, you will always find a very important thing that you will need in your future life. Let us say this tension here is T. In that case, this is T by 2. This tension in this string is also T by 2. And if this string is T by 2, so this string is T by 2. That means you are applying a force of T by 2 downward, which results in a force of T upward, lifting this body of 5 kg. In fact, this arrangement is a machine arrangement. This machine is called the chain pulley system. And those of you who are going into mechanical engineering will study more about this chain pulley system. This system you can apply to lift a heavier body by applying a smaller force, but at the cost of something. What is the cost? If you observe this very clearly, the motion of this body A is twice the motion of this body B, because this body is lifted by two ropes and this body is pulled in by one rope only. So in fact, if this is the acceleration A of the heavier body, then acceleration here is A. Because motion of this block will be twice the motion of this block. With this in mind, we can always write down the equations. Equation of the block A. In the situation of A, we write block A. For block A, we find the downward force is 4 kg. So downward force 4g minus upward force is T by 2 equal to its mass is 4 into acceleration is A. Exit 8g minus T equal to 16 A, or which is can be written as T is equal to third this equation as equation 1. Then we go to block B. Situation A, but block B. Block B, the upward force is T tension T minus downward force is 5G upward acceleration A multiplied by its mass 5. From here we find equal to 5A plus 1. Now if we preserve this equation as equation, if you solve equation 1 and 2, 1 and eliminate T, what you will find? You will find that 2A is equal to, find that, first of course you will find A. A is equal to G by 7, therefore, and so A is the acceleration, the question acceleration of the blocks A and B. So acceleration of the block B is A, which is G by 7, and acceleration of the block A is 2A, which is 2G by 7. One set of answer. Now let us go to situation B. Situation B. This situation. Now we are talking about this situation B. Situation B. In situation B, let us consider acceleration of this is A. Once again, since the rope goes round this and one end is fixed, acceleration of this block will be 2A. And if the tension here is T, then tension here is T by 2, tension here is T by 2, and tension here is T by 2. Now if we write these force equations, we'll find that consider the block A, situation B of A, situation B block A shows that tension T by 2 produces an acceleration of 2A on a mass of 2 kg. From there, we easily get tension T is equal to 8A. Tension T equal to 8A. And if we consider the block B, what we find downward force here is 5 kg, 5g minus upward force is T, tension T here is equal to mass 5 into downward acceleration A. So this is 5g minus T. So from this equation, value of T equal to 8A here in this equation, we find 5g minus 8A. From there we get 13A. 13A is equal to 5g, or A is equal to 5 by 13. So in this case, A, that is the acceleration of B, is 5g by 13. And acceleration of A will be, and acceleration of A is equal to twice the acceleration of B, that means 10g by the two accelerations in situation B. Now let us go to situation C. Let us go to situation C. Here again, if this tension is T, then this tension is T by 2. This tension is T by 2. This tension is, and this is 2 kg. This is 1 kg. Clearly given. And this is block B. This is block A. So in and 3, what do we get? In situation 3, we get from considering block B. Consider block B. We find T is the upward force. Downward force is 1g. So this is acceleration A. From there, we get tension T equal to fine. Now, consider block A. Consider, consider block A. Once again, we write the force equations. Here, it here it is 2 kg, so it is going downward, and it is going downward. And obviously, if the acceleration of this is A, acceleration of this is A, because the rope goes around like this, 2A. So here the force equation is downward force is minus upward tension is T by 2 is equal to 2 is the mass and acceleration is 2A. From here we find it is 4G minus T is equal to 9 by 2 is equal to 8A. Or rather, we find out the value of T, and we shall eliminate T equal to 4A. Now we take this equation and this equation. These two equations we take to eliminate A, eliminate T. Then we find that A plus G is equal to 4G minus 8A. Then we find 8A, this is minus, so this comes in the left hand side, 9A is equal to 3G. What we find, A is equal to G by T. So in this case, the acceleration A of block B is G by 3, and the acceleration of block A is equal to 2. So we find the acceleration of both blocks A and B in 3 different situations, right? So next day, once again, we shall continue with the numerical problems of Newton's laws of motion.